And I hope that the screen is shared, and I guess you can start.
All right, brilliant. Okay, thank you very much. Yes, I'm Joe Bailey from the University of Glasgow, and I'm going to talk to you a little bit about vitamin, which is a rapid Bayesian parameter estimation based on machine learning. So it's based on also conditional variation autoencoder. I'll talk a bit more about that in a moment. Okay, so yeah, so I'll go through a little bit of introduction about what we're trying to do and the motivation for it. I'll talk a little bit about conditional variational autoencoders and vitamin. And I'll go through some results and then a bit of a summary as well at the end. Okay, so what we're interested in? We're interested in CBC signals. So these are from binary black holes, neutron star black holes, or just binary neutron star signals. And what we want to do is estimate their parameters, right? So we want to estimate their mass, distance, or whatever else you want, really. We've obviously got a lot of these detections at this point. So through the last few observing runs, we've got around 100 at the moment, and there's a lot more expected in 04. It almost seems like we can already do this, right? We've got samplers and things which can estimate parameters and get Bayesian posterior distributions for each of these already. So what's the problem at the moment? The problem is it's quite slow. So using samplers like nested sampling or MCMC, they can take hours to days to run. And if we're trying to look or give alerts to our electromagnetic partners and tell them to point the telescope somewhere, we need to know an estimate of the sky position or estimate of some of the parameters. And front of those X-ray telescopes and things like that, you want to observe that as soon as you can after the merger. So like seconds to minutes, you want to be looking in the right place. And so if it's taken hours to days, that's not as useful. So currently there are fast all sky or methods to searching the sky, as we're saying, distribution on the sky for those to search there. But they're not a full Bayesian parameter estimation. They're just sort of ad hoc methods of it. There are other ways to speed this up. So there's someone else at the University of Glasgow, Michael Williams, who works on something called NESSI. Like names, things. But that basically uses machine learning inside of nested sampling to speed up, and they get an order of magnitude speed up. But this is slightly different what we're working on. But this is the basic motivation behind it. We want to speed up parameter estimation to get quick alerts out to electromagnetic partners. Okay, so vitamin. It stands for variational inference. So then it's not a very good name at the moment, but you can blame Hunter Gabbard for that. He's the one who came up with the name. So it was Hunter and Chris, which are the main people working on this, Chris Messenger. So they developed this technique, and it was published in Nature this year. So it's quite well established at the moment. So I'm just going to talk through some of the results of this and how it works, basically. So we're going to go on a bit of a detail into autoencoders and conditional autoencoders and variational autoencoders. So we start on the left with the simplest version of this. So an autoencoder is where you have a piece of data, saying this is an image of the number 2. You put it through an encoder to some smaller, what's called latent space, but that's just a smaller representation of your data, basically. And each of these encoders and decoders, and it's just some neural network. It's not so important what they are. You can sort of treat them as a black box. So yeah, with an autoencoder, you can press it down to a smaller space. And you have a decoder which goes from that smaller representation of your data back out into an image of some sort. And basically, once you train this, you can then use that latent space to generate new images. But if you want to have some sort of variation in those images, you can move on to a variational autoencoder. Or rather than just predicting a fixed set of numbers for your latent space, you can predict a distribution, right? So you can predict the mean and the variance of it's usually just a normal distribution, so a Gaussian. So in this case, you just predict the mean and the variance, and you have a distribution, and then you can sample from that distribution. And from that sampling, you get some sort of more randomization in that, so you can have different versions of your image. And in this example, you'd have a number 2 going in, say, and a number 6 might put put the mean and variance in a different place in this latent space. So when you sample randomly from just a uniform Gaussian here, you'll get different numbers out, is the idea. There's not too much control with that, which is why you move on to conditional variational autoencoders, which are basically the same idea, but you add a label in. So you add a label of 2 with that. So that way, when you go through the same process of training this, At the end, you can add a label of 2, and you can get 2 out, put a label of 6, and it'll give you a 6, whatever you want. That's the basic idea of, well, it's a very quick explanation of a conditional variation autoencoder. So I will we'll move on to the next slide. Okay, so what do we want to use this for? Okay, what's our goal of this? So we observe these are gravitational wave data. This is just a time series. At the moment, just a second long, so we're just looking for binary black holes at the moment. So we observe some data. It has some parameters as well, so masses, distances, sky positions, etc., which are each drawn from some prior distribution, which we can define beforehand. And from that, we want to estimate the posterior, or the Bayesian posterior distribution. And we can do that using what we call a target distribution, which is what our network will estimate, basically. And the goal of this, really, during training is to minimize the difference between the true posterior and our target distribution. And once that's trained and converged, we should have a good estimate. So the way we do this, there's this loss function here, which is just sort of the entropy between those two distributions, which is the thing we want to minimize, basically. But that basically just describes the difference between the two distributions. So how do we do that? So this looks a little chaotic, but I'll try and explain it. Basically, we split it up into lots of different distributions. Right? So we can't. So if we just go back a slide, we can't just predict this R distribution. So that theta there is the parameters of your neural network, basically. So we split that up into 2 to try and get it similar to the autoencoders that we had before. So we introduced a latent space, so this is Z, which we can basically marginalize over these 2 distributions. Now the reason for doing this and introducing this third function, so basically each of the neural networks in here is approximating some distribution. Right? So they'll take in a different set of data. So some will take in the data and the parameters. So this recognition function, we call it, takes in the data and the parameters and predicts some latent space. We have this other network, R theta1, which takes in the data and predicts the latent space. And the third one, which takes in the latent space in the data and predicts your output distribution. So that's your sort of Bayesian posterior, basically, what you want, your sample in the real parameter space. And there's 2 sides to this, a different way of training and testing, because we obviously don't have access to the real parameters when we're training, when we're testing. And so we don't actually need this slide of the network, so we can just go straight down the right-hand side. So there's a lot of maths which is sort of hidden behind this and how you arrive at this structure. It basically comes from this loss function, which is basically you go from the loss I showed in the previous slide to here through some maths, which I'm not going to describe. So just assume that's all okay. Beyond it, these 2 parts, which we call the KO divergence, which is the difference between the output of these 2 networks, and the reconstruction loss, which is your estimate of the loss. This is the estimate of the loss of your output distribution, basically. So that's sort of a brief description of the structure of this network. So what do we do? So we train on about 10 million examples, where in each training loop we augment on things like the sky position, the masses, sky position, the time of arrival, the distance, things like that. So we can augment the data to try and get more, because we need lots and lots of examples to train this. And training, well, I'll come back to how long training takes in a little while, but basically we have search over the full 15-dimensional parameter space. And so we just use the standard price as well, which Bilby and other parameter estimation groups use. And it can be run on 3 detectors. At the moment, it's at kilohertz for 1 second, but we can go to longer times and higher sampling rates. Just in these examples, this is what it was. There's not too much more to say on that part. So in training, what does it look like? Okay, so there were these 3. So the blue loss here is that reconstruction loss I mentioned, and the orange up there is the KL divergence. And then you just take the sum of those, basically, to get the total loss. So I didn't show too much other than it's going down. So this takes about a day to get to this point in training. Now we have this sort of this line which we're aiming for. So we can estimate the sort of minimum loss which we expect to get to by running a bunch of, so using density or other nested samples, we can get an estimate of what we expect that minimum entropy to be. And so that's what we're aiming for. So we're obviously not quite there yet, but a bit more training, a bit more tweaking in the network, and we'll be able to get closer to that. But at this point, what does it look like? So we can compare. There's a bit of a large plot with lots of things on it. But the thing to focus on is that there's two distributions here. One is an output of dynasty, so that's the sampler, and one is the output of vitamin. So that's red and dynasty blue. And they compare really well, right? So they're quite close to this particular example. The difference being is that dynasty would take hours to get this, and vitamin does it in fractions of a second. So it looks quite good for a single example, but obviously that's not quite good enough. We need to compare it to lots of examples, basically. So one way of testing these stereo distributions is what's called a PP plot, which basically describes if it's statistically consistent. So it's basically saying what fraction of your events lie within some confidence region of each of the marginal posterior distributions. And if it follows a diagonal line, then 10% of the time it will be in the 10% confidence interval. That means it's statistically consistent. So this is one of the common tests using parameter estimation, and it agrees quite well. I mean, this is compared to other samples as well, so it's very comparable to those. One other way to test this is what's called the JS divergence. So that's basically the KO divergence. It's obviously directional, so you can swap the order a bit and take the sum of them. That's what the JS divergence is. That's a comparison of the two distributions. So here we show the comparison of dynasty with lots of different samplers. So these are various samplers used in CBC parameter estimation. So CPNS, PTMC, MC as well in there, which is the worst one here, and vitamin as well. They're all compared to dynasty. So you can see from this that vitamin is actually quite comparable to other sampling methods at the moment. But obviously it has the benefit that it's very, very fast. So I think I'll leave that there. So I'll come towards the end. So we've identified a problem in the CVC group for parameter estimation, where we wanted fast estimates to send to EM partners. We use vitamin to get Bayesian posteriors out of this, and it can do it in fractions of a second, so substantially faster than any other method of filming. And we've shown that it performs similar to other samplers as well. So there's a lot to do at the moment. So these examples were from Gaussian noise, basically, covered to whatever PSD you want. We obviously want to extend that to use different PSDs as well as using real data. So that's work which is currently, I'm undergoing that at the moment. Hopefully that should work okay. We also want to extend to BNS signals because that's really where we want to use this, because that's where we want the EM telescopes to go and have a look at BNS mergers. So that's just another step to add, as well as other waveform models, and there's lots of extensions to this project. But yeah, there's a sort of a proof of principle in this paper in a way. So I think I'll leave it there. Is there any questions?
Questions?
Thank you. Very interesting talk. I have actually two questions. The first one is, what is the difference between variational AE and conditional? I didn't understand this. Yes, this one.
Okay, so variational autoencoder will just take your input data, will encode it into a mean and variance, and then when you want to generate a piece of data, you'll sample from a unit Gaussian in your latent space and just pass that through, and it will give you, it could give you any, say in this example, it could give you any number, 2, 3, 4. You don't know, you have no control over that. Whereas conditional, when you train this, you give it data and a label. You train that, and it'll do a similar thing. It'll place it at a different point in the parameter space. You'll still sample from a unit Gaussian and also give it a label. This way you have control over the output, so you can pick the.
So this is what you're using side information in this conditional autoencoders, right?
Yes, yeah.
Okay. And what is the motivation for this passage from autoencoder to variational autoencoder and then to conditional? First, how do we know that variational autoencoder will give better performances? But autoencoder? And how much better?
Well, I think it depends on the problem. So they're used for different things, right? Autoencoders and variation autoencoders. If you don't have variation in what you expect to predict, then you'll probably use an autoencoder, and they're really useful for that, right? So I think they're sort of used for different problems. I was more just illustrating this as a point of this is how they evolved.
So for this purpose, we cannot use ordinary autoencoder.
No, we need the variation there to generate a distribution, basically.
Yes. Because when you do parameter estimation, what is important is not the estimate of the parameter, but it's the error around the estimate. So you need a distribution.
Yeah.
That's the point.
Yeah.
Okay, and how large are these their structure?
Well, we use various different ones, but usually we just use ResNets, but quite small ResNets, not the off-the-shelf ones. They usually have around 15 million parameters in each of them, and we have 3 separate ones. So they're not huge, but relatively large, if that answers your question.
Okay, thank you very much.
Was other few questions? I think I will go on that side just because it's easier.
Hi, thank you so much for interesting work. I have many questions, but I will ask 2 of them, if that's okay.
Yes.
So my first question is, well, if I'm not wrong, NESI also relies on normalizing flows?
Yes, that's right.
Okay, so what are the benefits of using autoencoders instead of normalizing flows?
That's a very good question. So I mean, they can both be used for parameter estimation. There's even another group, I think it's AI there. They use I think it's called Dengo, their package, which does essentially the same thing as us, but using normalizing flows. So what are the benefits of autoencoders? Is a good and I think difficult question. So I mean, normalizing flows have some sort of limitations in that. Just getting a bit technical with that, but they have so your input distribution for a normalizing flow is usually a Gaussian, right? And you transform that, and I forget the word they use, but you can never properly separate distributions with that, I think. Whereas in autoencoders, I think that's less of an issue. Although we have lots of tricks and stuff to do multimodal posterior as well inside this. So I'm not sure that really answered your question at all there, but they're both quite useful for similar purposes, I think. I'm not sure if Philip has an answer to this as well.
Yes, so the main problem with normalizing flows is the dimensionality. So as I said, like the latent representation is basically the same size as the input data, and when you would like to, for example, process large inputs like hundreds or thousands of features, that's actually quite tricky to train normalizing flows, also because of the limitations of hardware use. So usually, like normalizing flows are used in applications up to some hundreds of features, and you are also not reducing the dimension. Like in the case of variational autoencoders, which as an autoencoder, it's primarily used to reduce the dimension of data. So sometimes it is a significant advantage over the data, but it's again problem specific. And also in case of normalizing flows, as you said, yeah, it's just like a set of Gaussian distributions. It should be in principle like invariant to each other. They might not be, like in some cases, as I said, also in my project, sometimes those, let's say, Gaussian representations were the perfect ones. So then, assuming that they are invariant, following the analysis, might be tricky because interpretation of results is not straightforward either. So sometimes, yeah, these autoencoders are a safer choice, at least for now, because it's, I would say, much better known algorithm. Because it's, I guess, a couple of years older also. There's much more applications. That's at least my understanding of it.
Okay, thank you so much for the detailed response. That's very good. Okay, now I have a better understanding. So my second question is, do you, well, I guess not because it's in an early stage, but how was the comparison with, aside from Dynasty, like other people that use the normalizing flows, like for instance, Strange work that's in the same slide, in compared with the SNR, right? Like how low could you get?
So we don't have a direct comparison to those yet. I think that's something we'll do in the future. Certainly if there's MDCs and things happening in the future, I think that'll be a good place to compare. But yeah, at the moment we don't have a direct comparison with them, unfortunately, yeah.
Okay, so keep me in the loop.
Definitely will.
Thank you.
It's a super interesting work. Actually, the question concerning the time, so I don't see any artifice except the autoencoder, so I guess it's super fast to produce an output, no?
Yes, yeah, it is.
So it's out of seconds, so still minutes?
So to generate a full posterior, it depends a bit, but it's about 0.1 seconds, sometimes less.
Or comparing to the traditional method, it's super.
Yeah, so yeah, compared to ours, it's negligible. Yeah.
Still concerning the time, do you have an idea of how long do you need to train that stuff?
Yeah, so we're not entirely sure, but generally we've got pretty good results. A day, a couple of days. We've got things trained for weeks as well, but I mean, it somewhat depends on the architecture of your encoders and decoders as well. So we're still trying to optimize those to make it train as fast as possible. But generally, a few days to a week at very most is what we've needed so far.
Okay, because so the previous work I mentioned earlier, so with Exponus, if we want to apply that to neutron star, the problem that appears is that the training for the neutron star can take way longer.
Yeah.
So I guess you will face also the same problem. Do you have perhaps an idea how you can find a way to not have this problem?
So with neutron stars, well, we haven't actually come to that yet. We're sort of starting to think about it and how to actually use that. I mean, there's a lot of ways to reduce the dimensionality of the problem in neutron stars. I think people have used like his ROQ and things like that. Initially, we're just thinking of basically sampling it at different rates. So you just having slower rates early in the inspiral, and then higher sampling rates around the inspiral, around the merger even. Yeah, low sampling rates around the inspiral. So that's really all we've got so far. But obviously, we need to test those out.
Okay, thank you. Nice idea. Nice work. Thanks.
Just one question this time, I promise. Also on this plot, I didn't understand something basic. So these plots all sketches all look symmetric. You put in an image, you get out an image. But what you really do is you put it in time series and you get out a velocity data. So how can you say which of these two labels the data corresponds to?
Yeah, so this structured a little bit different to this. Obviously, it takes us another step, but in a sense, our label here is our data, and the thing we're trying to predict is the parameters. So it's sort of switched around for us in a way. Obviously, it's a bit more complicated because we've added extra networks and things like that. Does that answer your question?
Okay.
Yeah.
Okay. Seems there are other questions, so let's thank again our speaker. So the next one is Alberto, and I have no idea how to get to the slide. Okay, yes.
Okay. Okay, great. So hello everyone, and thanks for the occasion to present our work here in Valencia. So I will present a work on core collapse supernova detection and classification using two specific types of neural network, in particular convolutional neural networks and long short-term memory networks. Both have been already nominated in previous talks. So thank you for doing my presentation work. So the very first slide is just for non-gravitational wave people. So gravitational waves are a solution of the Einstein field equation, and they can be seen as a perturbation of space-time in the linear approximation. Do we have also a pointer here? Okay, great. So we have a lot of different possible sources for gravitational waves, and in particular, we focus with terrestrial interferometers such as Planck and Virgo on binary collapse of binaries, and on other sources such as core collapse supernova or isolated neutron stars. So the other side is not the astrophysical part, but the instrumental part. So we have other types of signals which are due to noise, and we call them glitches when they are transient noise bursts. And then we have long-lived disturbances, which set really the shape of our sensitivity curve in the interferometer. These are considered stationary, even though they can change in time. So you have already seen similar plots. Here on the right, this is an old plot actually, but all a number of detected sources, binary up to now, unfortunately. And here you can see the time frequency representation of some of the signals in the first gravitational wave transient catalog a few years ago. So the standard technique for compact binary collapse detection is the matched filter approach, which basically means we use a template and try to match it to the data. And here you have an example of whitened data. And this relies on a good knowledge of the phase evolution of the signal and a large template bank, which depends on a number of parameters, such as the masses, the inclination of the system, the position in the sky, and so on. It is the optimal technique for stationary Gaussian noise background. On the other hand, it is very computationally extensive. So when we don't have a good knowledge of our signal, such as in the case of the sources I will present, we cannot rely on matched filter. So to the sources, core collapse supernovae. They are different from binary mergers because they have a lower amplitude, first of all, so we cannot observe them up to very far. They are rare in our Milky Way and in the neighborhood. And most of their energy is not in gravitational waves, but in other emissions such as neutrinos. Okay, they are also a good multi-messenger candidate for the future because we have the neutrino emission, the gravitational wave emission, and the electromagnetic emission. There are different potential explosion mechanisms, and the bad news is that the most probable is the one with the weakest emission, which is the neutrino mechanism. So what is the problem with the core collapse supernova gravitational waves? Is that we cannot model exactly the signal. We can predict the presence of some emission mechanisms, which give us a signature in the time frequency domain, but we cannot have an exact template bank. It is a largely stochastic process. We have convection and we have all sorts of physical mechanisms involved, which cannot allow to use matched filter. So we use other methods. And here I want to show an example of a number of simulations, 3D simulations, which are computationally expensive to do, and produce some examples of gravitation waves from this kind of sources. And what we can see in the time frequency domain is the presence of some peculiar features. The most prominent is generally this oscillation modes of the proto-neutron star, which is forming during the collapse. And then we have some lower frequency characteristics due to the so-called semi-accreting instability, shock instability, and convection. And as you can see, different simulations give different peak frequencies and different characteristics, especially in the time frequency domain. So the idea here in our project was to build a sort of a full pipeline, which uses a noise background, either simulated or in this case, real noise from the O2 dataset, add some of these waveforms from the simulations, and then runs a trigger generator, which is based on the wavelet transform, which is used to find the signals in the data as transients, and then classify them with a machine learning classifier. And that is where the CNNs and the LSTMs get involved in the picture. Okay, just a short word about the library used. So it's this wavelet detection filter. It has a Docker implementation. So if any of you is curious, just check the website. And it is used after fixing a certain threshold to get triggers in the data. It is also carrying out time domain whitening, which allows to clean the data from the noise, to whiten the noise. Okay, back on the networks, we're using convolutional neural networks. I won't spend too many words on this because it's already been mentioned. So they're used because they are good at picking up patterns in data on different scales. And in particular, we use 2D CNNs on spectrograms and time frequency representations, and 1D CNNs on time series. On the other hand, we also tested these long short-term memory networks, which are a particular class of recurrent neural networks, which have a more complicated structure, which was designed by the original authors to avoid the so-called vanishing gradient problems when you get a deep network. On the other hand, they were created for to follow patterns in time series data, but they are generally harder, from my experience, to train with respect to simple convolutional neural networks. The hyperparameter tuning can be a bit challenging, and as mentioned previously in the discussions, we see that for longer time sequences, such as those of gravitational wave data, their performance tends to fall off pretty fast. Okay, so this is the full data set we used for training. And I won't go through all the models. Some of you in this room are experts and know them, so I will get questions later if you want. And then the injection mechanism, for those of you not in gravitational wave science, we have different interferometers, and the idea is that we have two polarizations of the gravitational wave and two functions which give a weighting pattern for the two polarizations, depending on where our source is located in the sky. You see all these dependencies from the angles. These are right ascension, declination, latitude and longitude of the interferometer, the angle of the interferometer arm, the angle between the interferometer arms, and the orientation of the interferometer with respect to the to a meridian or equator. I don't remember exactly which one of these. And here you see the structure of the sensitivity of the antenna patterns. So the idea is we inject these signals and we vary right ascension and declination. So to have to study also the effect for different sky position. So we took 44 segments of the O2 science run, injected a number of core collapse supernova signals, and we chose to inject the same number of signals for each of these different waveforms, which leads to an imbalanced dataset. Why so? Because the different signals have different amplitudes. Some of them are even not exploding during the simulations, so the energy release is quite different. On top of that, we also have noise transients, glitches, which we categorize as a single category in this specific study analysis. As I mentioned previously, the SNR distribution of the signals will be affected by the antenna pattern, so where our sources will be, and by the detector sensitivity, because we're using a 3-detector scheme. So we are testing individually on each detector, the 2 LIGO detectors and the Virgo detector, and then also on the network of all 3 detectors combined. Okay, I mentioned that matched filter was the best solution for stationary noise. Technically, even on real detectors, the PSD is not always exactly stationary, so there can be some variation. Some noise lines can increase during even a single lock. And so we assume the stationary PSD when whitening the data. Okay, so here you see an example of a big glitch you've already seen in previous slides, and the color palette is not working very well, but of one of the signals. Okay, yes, I'm sorry for these confusion matrices. I hope maybe you can open the presentation on Indico and you can read the numbers also from here, because I will, actually. So here is a comparison of different machine learning models on our data set, because we are running a multi-class classification. So in our case, the label is not simply noise versus a blip, a transient versus a supernova signal. In this case, we're even trying to individually find which of the different models is the signal from. Okay. So I want to mention a few things. The training time is different for the different networks. Obviously, one DCNN is the faster, while the long short-term memory network takes a much longer time. And also, we needed to train it for a larger number of epochs for it to converge, and you will see a later plot about this. Okay, so I'm sorry you can't read the numbers, but what is clear when looking them on the uploaded presentation is that higher amplitude signals are better classified. And this is also affected by what I said previously, that the dataset is imbalanced. For instance, you see basically all of these Anderson signals are misclassified. They are very low amplitude, and they don't trigger our pipeline basically ever. So we can sort of discard them from the analysis. On the other hand, the best classified signal is the highest amplitude signal, which is the Powell, which is a rapidly rotating Wolf-Rayet progenitor star of high mass. Okay, so here you see the evolution of the training loss, and here you see the wrap-up of all the different models for all of the dataset. The spoiler is that for this Virgo dataset, results are much worse. We expect this because we're injecting the same signal in a much lower sensitive interferometer. And we use the true positive rate as a metric reported in this table. Okay, another massive confusion matrix plot. Here, as I mentioned, it's the Virgo confusion matrix. And what you can read here is the data set for Virgo. And with the number of instances in the data set. And what you basically get from this picture is that only the very represented classes are well classified, while most of the other are not classified well. And this is the reason why, for instance, the network is classifying all of these low amplitude signals as either Powell or, yes, or as this Powell signal. Here you see the representation of the histograms of the number of signals in each of the different waveform model datasets. And what you see in the x-axis is the SNR. So you see that there is this pattern where you have this red histogram, which represent the misclassified signals. And even on the Virgo dataset, you see that the higher SNR signals are well classified when for a high amplitude waveforms models. But you see that all of these other classes are bad classified. Okay, so what we did in the end, this is maybe the more interesting part, is to assume a 3-detector network and try to classify the signals using information from all of the 3 detectors combined. You can do this in multiple types of ways. You can take the input initially and feed it all to one network, or you can use the merged output from the networks. You can choose to weight them based on their sensitivities. There's lots of types of things you can do. In our case, we use the merged probabilities at the end of the network. So we added a final layer, basically. And in this case, what you see is that the accuracy seems lower in some way to the single detector LIGO cases, but you have also to take in mind that in this case, we're using only for the training set a reduced data set, which is that of a triple coincident trigger. So what we could technically do is to just trust the more sensitive interferometers for the trigger time and increase the dataset size. Still, it is quite robust for it recognizes noise transients, because I think it's 97 or 98% correctly classifying noise bursts, and pretty robust also for high amplitude signals. So that's my last slide, actually. So I'll take questions.
Thanks. I know very little about supernova searches, but have you thought about using a coherent trigger generator? Because maybe CWB would work for this?
Yeah, technically it's possible. Yeah.
Next project.
Hi, thank you for the talk. It was very interesting. So I think my question is more how you deal with imbalanced data sets. Because I think that's also a problem that we're having that car with all the different type of glitches that
Sorry,
in the vector characterization.
Yes.
Because in the end we have like very different glitches, and some we have a lot, some others we have very few. So I was wondering how you could, for instance, penalize your network to deal with this.
Okay, so my point of view is that you cannot use the same approach with glitches and supernovas. I mean, here, at least I cannot give, like, for glitches, we have, we can study the occurrence of the glitch, okay? And that affects, in my opinion, the data set, of course. But in here, in this case, with supernova signals, you can say that one model is more probable than the other. I mean, you can, that one mechanism is more probable than the other, but you cannot distinguish, for instance, between two of these, I don't know, Powell waveforms, unless you have some information on the population rate of the different progenitors, of course. So what I would assume is that you would have generally you should have a larger data set than the one considered here. The SNR distribution, probably I would have it the same for all the different data sets, so do some kind of normalization. This data set is also imbalanced because we chose at the start of the project to have one fixed distance for the signals. And this obviously will make all the data set amplitude dependent. So that is the thing here. So we fix the distance, means that more energetic model will be more present in the data set. But yeah.
Yeah, so just one thing, what I meant is more that maybe there's a way to analyze your network to make it balance your data set in that sense. I'm not sure if that will be possible.
Yeah.
Yeah, exactly. So maybe that could be something to take into consideration.
Yes.
Again,
yes. Yeah, I perfectly agree. But still, I think, for instance, we would have more some classes which need to be still represented more. I mean, it may work. I assume you meaning that we are penalizing more for some class with respect to another, right?
Yeah, especially the ones that are misclassified.
Sorry?
Especially the ones that are misclassified.
Yes, I would assume so.
Well, actually, I have two questions.
Sure.
One related, so there was at some point in some of the previous slides that it was written like this one, best way. So what means best way? It's like I would expect like the best accuracy. I don't know. You have some mechanism to stop the training? No.
Yes.
Okay.
Yes, one of the different.
Accuracy, whatever.
Yeah.
And another thing that has nothing to do with actually this project, it's a general thing. As far as you know, there is like an independent way to check if one of these models it's more it's better than the other in the sense. I guess sooner or later we will have some supernova explosion, and there are neutrino detectors and other detectors. They can rule out some of this model, or they are only focused on gravitational wave. They have nothing to do with other. They have to do with the mechanism, I suppose.
I must confess, I'm not an expert on the actual simulation, but all of these are, for my knowledge, they are all neutrino-driven explosions. Another thing which is more feasible at the moment is to distinguish between the different explosion mechanisms.
Okay.
That's more
feasible.
Yes, that's really more feasible. Only based on the gravitational wave emission. Yes.
Okay. Since there are no other questions, so let's take the speaker again. Let's go on.
Thank you.
Okay.
We can speak with him, but our camera is not shared, and that's it. Okay.
Yeah, we don't need to share the camera.
No, we don't need to share the camera. So.
But I don't hear the voice of Fabio.
Yeah. Can you put the people? Exactly. So, hi, Fabio has no mic now. Fabio, can
No,
you?
I'm here. If
Okay, now I can hear
you a
you.
message through the chat, but probably
Yeah, I am.
now I can also
El
appear.
volumen está muy bajo.
Yeah, it's because we lost the sound on this speaker. Yeah, something happened with this camera. I don't know.
Yes, one moment, we have a technical problem.
Yeah.
Ah! We found out the reason of the problem. Good. It works better when it has electricity. Okay.
Now you have the light.
I didn't notice.
Uh-huh.
Let's see.
Try to speak, Fabio. Let's see if it works better.
Hello, how are you?
Okay.
One moment.
One moment, please.
¿Será el HDMI? No.
No. Maybe now it's connected, right? Okay. Now it's connected to this speaker.
Okay. Fabio, can you say something?
Yes,
Okay. Yeah. Okay. I think, Fabio, you can share your screen.
Yes. And this is not working. Maybe I need. Okay. Okay. Maybe now.
Yeah. Okay. Yes. Put it full screen.
Can you see it?
Yes.
Okay.
Yes. So you can go.
Okay. So thank you. I'm happy to be with you, but a little bit less happy for not being there in person with you, with those of you who are there. And as told, this is due to the fact that in this period I am really very busy. So today's topic is open challenges for the application of deep learning to distributed mobile sensing. Want to say? I basically want to share some ideas and also some ideas about work which has started but still need to continue for a while, I think. So I think that by now we all know about robotics. We know that a lot of the nice stuff can be done, but also we should not be too much enthusiastic about what can be done because advanced applications like those that we have seen in the DARPA challenge, so human-like humanoids, things that you also can see on YouTube, are actually still far from being as stable as you might, as you need for example, scientific application or environmental monitoring or noise characterization. So there are things that can be done and things that are not easily done. this is due to a number of reasons, but one of the main reason is that in robotics, the scientific methodology is somehow weak because usually you want to show that you can do something very, very cool, like having a humanoid robot doing parkour in a lab. But then you don't care a lot about how many times you can do that. And there are some fundamental issues regarding how robots should be developed. However, why robotics it makes and deep learning have reason to be exploited together and can probably have probably they have a synergistic effect. So deep learning actually also in robotics helps to solve some problem. We all know about a famous Go playing system by and then AlphaFold, a synthetic system to synthesize proteins. What is relevant here is still this, that it's true that Go is much more complex and difficult than chess, because you see that eventually, so you can give for perfect information games an approximate dimension of a recursion tree where you should explore to find the optimized solution, so how to win the game. So there is a significant increase from Go to in comparison to chess, but still AlphaGo, which is the first example of this approach, which is basically, as I think many of you know, a merger of Monte Carlo simulation and deep learning. It's still a perfect information game. So it's still, so to speak, a game. So in comparison to social, for example, you know that the long-term objective of RoboCup is that by the year 2050, a robot team should win the social world championship. The main difference is that real life application of robots are not perfect information games. So you haven't a well-defined problem with a number of deterministic choices that you can do. And then you can explore with a Monte Carlo simulation. But in essence, Go and chess are different implementation of the same game, while the interaction in the real world, it's another game. So this, I think, can be boring if you heard already this kind of comments, but it's important because one thing is the robotics research, the basic robotic research, which is, I would say, my main interest. Another thing is the application of robots to concrete problems. The good news is that if you think to ET, or if you think to Virgo or LIGO or Kygra, they are not perfect. So having robots moving in these tunnels, for example, is not a perfect information game, but can somehow be reconduced to it, because after all, if you assume if we are in a semi-structured environment, so like inside a building or a tunnel, the number of uncertain parameters that you need to deal with while controlling the robot, it's much lower. So I don't want to tell the story again of seismic noise, but it is I think accepted the idea. Why I think we all share the idea that if we could characterize seismic noise, for example, but also other kind of noise like electromagnetic noise or acoustic noise due to human presence, we could actually clean the signal more than it is possible today. What is also in what we can do, I would say that if we think about how these things are done so far, is that you usually prefer to use, but the reason is that they are more easy to manage huge arrays of fixed sensors. Here we are talking about what could be the next stage, which is to integrate the fixed sensor for noise characterization with a network of mobile sensors, because basically if you focus on the seismometers, but it's true for all the different kind of noise that you can be willing to chase. The difference is that part of the robots of the sensor can move can move according to a predefined trajectory, so speed, velocity, vector changing over time. And they can actually give you much richer information than what you can get with a fixed sensor. And they can also, in principle, give more accurate measures, no? Because if you move your sensor, you can also adapt in real time, and the characteristic times over which you have changes in the seismicity are what in the roboticist and control jargon is called as soft real time, so not very demanding real time. So you could actually have this adaptive network. So in principle, so by applying sophisticated versions of the Bayesian methods, you could have much richer information. This is my favorite example, and is what I think at some point we should try to implement, which is having a multisensory data fusion, so sensors of sensing for different kind of signals, for example, noise, seismic and electromagnetic, which can move. This has been actually be done in some system like this answer to already sometimes ago, I would say more than about 10 years ago. However, with systems that, in comparison to what we should implement if we were planning to use mobile sensors, so robot sensors, to characterize noise in gravitational wave detection, are still simple. I will show you a picture in a minute, but it was a drone plus a mobile robot, ground mobile robot, no more than 5 pieces or up to 10 different robots. What we are dreaming here, what we would like to make to use is a network of tens or even hundreds of such robots that immediately we realize should be comparatively cheap. So we cannot use each robot cannot cost like it was in that old example, 20,000 euros or 10,000 or even 10, 20. And the point is that if you look to the software structure or of this kind of what we could implement, you have two pieces where you have many you may use deep learning, and these are, so of course we have no time to go into deep detail in this kind of application, but if you look at this schematic of a data fusion system in this distributed, decentralized, multisensory fusion architecture, you see that you have the obvious thing like the filter of a channel, the multiplication of a different measure about the same stuff, same signals that you, because in our case the noise is the signal that you put together the convolution to do perform. So you have a number of things which are pretty straightforward. Other things are less. For example, the likelihood model, so the model of what is more likely to be true than not, and the preprocess and feature extraction. Here is where you have a lot of freedom in the choice of parameters, and as a consequence is where you may need a learning system to choose and to learn the proper setting of the parameters. Yeah, as I anticipated, you see how small was that system now, because you had an air vehicle, a ground vehicle, and even a human. But this could actually be what we should look for, because it is this is linked to what I've shown you at the beginning about the DARPA challenge, because we are still far from not even human life intelligence, but even dog-like intelligence. So the idea is that you will always need a loop where you have some human. The big change with respect to us, but I think also apply to the utilization of machine learning, of deep learning to detect signals like waves, gravitational waves, is that the same person can do much more work. And since we receive, and we will receive in the future, more and more data to analyze, the possibility to be helped by deep machine and deep learning methods to identify the sensitive patterns in the massive data flow, and also having this kind of stuff of robots deployed in the environment to really analyze online what's happening in the air close to the detector and underground under the detector, and even inside the detector, because as we know, people working in a room can create some noise. Also, but this I think I already told you, but it's never, for those who didn't heard it already, what is a noise for the people looking for gravitational waves is actually signal for people looking for seismic activity or trying to characterize the geology of the underground close to the interferometer. So actually, again, in principle, the interferometers of the scale of current gravitational wave detectors could be used for geophysics, for underground characterization. So more in detail what I was anticipating, so as a summary of this part, we should explore these possibilities here. We talking about sensors, you know, InnoSace, and a promising one that we already implemented together with Tomek Bulik's group into a single robot platform. Should be integrated into a network. So how we build this this network? What here I will spare you the details, but what we need to do is model the signal, and in this case, the signal are the noise signal. So the seismic signal or the electromagnetic signal or the acoustic signal by some kind of Gaussian process session. We will need to follow, this is the main architecture of the system that we envision. We will need to optimize the position, continuously optimize and adapt the position of the sensors on the basis of the maximization of information gain. So we look for the places where more things happen, where the signals change more over time. And then we needed to coordinate the robot and allocate the task. In all these modules, a promising approach, because they've been tested in similar situation, is to have to tune, for example, the regression by a learning system, to optimize the information gain by learning system, and same for the optimization of the coordination of a different robot, no? Because if you only used the information gain, all robots would go in the same place. So you needed to also not only to implement a system which drives your sensor in a promising place, but also avoid to put all the robot in the same place. No? So this is the main aspect of a multi-robot coordination and allocation. What I want to say is that, and it was this is related to the very first few slides, is that this is not a kind of robotics problem which can be compared to doing parkour with a humanoid robot, and not even opening a door with a humanoid robot. This is a well-known technology that could be used already. Then we could, for sure, improve over time, but a simple application of the answer model with supervision by reinforcement learning or imitation learning. So some application of imitation learning. I hope to have time to show you some different application of imitation learning in conjunction with stochastic control, like the belief space planning. Is all stuff that could be used tomorrow. What is needed is software integration, software development and integration. So it's maybe less interesting from robotics or AI research point of view, but is definitely a stable platform that could be developed for the purposes of both gravitational wave detection and geophysics investigation of the underground. This is was last year, was the Subterranean Challenge, and again by DARPA, the US Military Research Agency, which organized the DARPA Robotics Challenge. And this was much more successful than the humanoid challenge, because whatever you think of these underground tunnels, they are much more structured than working in just the problem of walking in front of a door of a warehouse and opening it. As strange it may, as strange you should, because the problem is much more structured. No? So the fact that you have this tunnel already constrain the values, for example, of the distance of the walls or of the ceiling. And this was quite successful. So actually all the teams were able to do interesting work. Then, of course, there were winners and losers. But it's really unfair to do this kind of summary. But the summary of the DARPA Robotics Challenge with humanoids was, oh, we still have a lot of work to do. In this case was, okay, yeah, it's time for engineering more than, there are research issues, but as a whole, we can say that navigating a tunnel is feasible most of the time. So if you always have exception, but it's, okay, this problem is kind of, I don't like to say that the problem is solved, because you never solve problems, because as soon as you are able to do something, you can dream and plan to do something more sophisticated. But this is, so I think these two challenges had very different results. One was, it's really a mess, we still don't know how to do it in a robust way, and this was, okay, still some problem open, but we, the standard techniques that you use for navigation can work underground. Another, and this is the not so advanced level of activity on this, because what we could do so far, and this is a cooperation between my company and AstroSense, is to build a prototype low-cost platform using ROS, which is a way to avoid to write tons of software from SLED, and they use as a brain a Raspberry Pi, so really a very, very cheap hardware. And this is able to move into Tomek's lab in Warsaw. Of course, we need more than one of these. Huh? It is designed to put the geophones that have been already put in Virgo in fixed form. So we are kind of ready. And the logic that we follow is the same of a NASA's insight. So we basically take the sensor and with a crane we put it on the ground, and it works. So we have, so what I want to say is that, okay, don't buy a humanoid to take care of your home, of your house cleaning. Don't buy a humanoid to help your old parents, but you can buy a stupid robot like this one to take measures of vibration or also presence of chemical. This is not interesting in our context, but so if you think to some place in Ukraine, you may think of sending a robot to see if there is some undesired chemical. So this is something that can be done. However, when I think more in a longer perspective to the utilization of machine learning and deep learning techniques in general in robotics, but in particular in this kind of a system that we are envisioning and that we hopefully one day will develop at at least at some demo level, is the kind of a time series, because you may have noticed that when I've shown you the schematics of a distributed way to integrate data in the multisensory fusion algorithmic machine, I insisted in say, okay, I will. My idea is that I will use a likelihood function, and I will update it by limitation or a super reinforcement learning system. This is a conservative approach. So when I presented you this those ideas, my idea is to limit the risk and to have something which works for sure without a lot of hassles or of work. However, we may want not to fine-tune a classical likelihood function on the signals, but we may want to learn it. And here immediately find one thing. Another thing, we may want to use our mobile robots not in nice tunnels or on a nice on the nice grass around the detector, or maybe even 5 kilometers from the detector, but on a nice floor in the airport or things like that. No, if I would like to put these mobile sensors in a wild, then I immediately have some problem. For example, that are the same problem that we have in analyzing the data stream from the detector, but maybe even even more hard, no? Because one is basically, if you think to this different source of data, geographically distributed, changing over time, and typically are image-like. So you have matrices, and these matrices as well depends from your perspective. So what you should, in principle, be able to learn is a time series, a multiple time series, because you want to fuse them with where the contact can be, if you want to be again conservative, in matrix form, but it could be also in tensor form. The second point is that, and this is ubiquitous when we wanted to apply to physical systems, but I would say it's the general addressed problem by gw1. When we want to put machine learning on physical system, another thing, the first thing is time series, rich time series. The second thing is that still those data are not really big data in the sense of Facebook database data or Google image data set. So it's a lot of data in comparison to other applications, but it's still not as big as the data set where we know that you can easily training, for example, a language model. No? So you can talk to Alexa, as we know, because behind Alexa you have a huge voice recording data set. The other thing is that you don't learn in an abstract space, but you learn on the complex manifolds defining the physics underlying your system. And in this case, so you have the physics of a robot, but also the physics of what you are trying to measure. I was talking about information gain to drive the allocation. Okay, so this means that I should, in an advanced application of what we are, what has been described, I need to be able to follow gradients of information matrix. So you can start from the Shannon entropy, but when you have other more Sallis entropy, you have a different kind, and it could be a stupid game to invent your own entropy measure, but they again are on complex manifolds, in particular complex if you work in the frequency space. And we have the course of dimensionality. So and so we enter into this kind of issues, manifold learning. What is encouraging is the fact that what is known now a known fact, that the accuracy of your system increases with the number of hidden layers. What is not encouraging in this picture is the fact that you see that the curve at some point you have diminishing returns. Okay, we know we have mathematical. So this is a slide that I stole from Giorgio Metta, who is, apart from being a very active researcher in intelligent robotics, is now the scientific director of AIT. So what's really happening is that we have a dramatic increase in the number of parameters of a working models. No? So and if you divide this 175 billions by thousands, you already see that we are in the hundreds of millions to build a top of a top level learning system. So this is clearly a limitation. So it's a clear hint that deep learning methods are powerful, but we need some new insight to use them. And this is GPT-3. GPT-4 is here. Then I recently read of another system which is almost as good as this one and only stays here. So there is some space for improvement. This is the point. Yeah. So just to conclude, I don't want to go into this because this would require another. Actually, if we target these more advanced problems, we should look at the relation between dynamics and information, and this is a new approach to robotics. But the bottom line is that, that physics matters. So that is not a joke. And talking to a group where many are actually physicists, it's also could even seem flattering. But the fact that we haven't a clear, if not in some frontier research, we haven't a representation of physics into deep learning systems. And I think we even don't, when I talk about manifolds, it's because I think we should use indirectly physics and so define the space where the optimization of the approximation of the deep learning algorithms work. This is a very, very serious problem, and I think it's the core problems of this action, and is still will still be a core problem in the next 10 years if we are lucky. Yeah, I wanted to skip this part because it's about my work to try to clarify those aspects. I just to see that some work has been done in this direction. A lot of work has still, for example, I think that a promising work in this direction is this application of imitation learning for the control of an arm. In that case, was an arm in an unstructured environment. It's quite, is not reported here, but there is also an application to use it to govern surface, an autonomous ship on the water, and can be easily adapted to the what we have in mind. So it could be the level 0 of the application of these methods to the multisensory network. What we can do with a prototype built with Tomek is that we can govern, force him to move around a big group. There is a huge research space because AI is here on the left, and so you have a solution or partial solution of algorithmic problem in the space of perfect information game. So it's ongoing. Many people are working on this, including myself and others, is taking a robot and optimize it. And it is what I think we should do in a reasonable future, to apply robots to perception of noise. But there are a lot of very interesting problems if you accept that the robot can be soft. But this, I think, is not of immediate interest to our community. So yeah, I have some self-advertising paper about which your opinion is welcome. And so thank you.
Thank you very much.
Fabio, tu ci senti? Cioè, suppongo che mi vedi, ma ci senti? Do you hear us? No.
I hear you. Yes, yes.
Ah, okay, bravo. So, are there question, comments? Maybe very different. No.
As it happens, you have two leaders of the working group.
Yeah, on the other side.
Would you like to comment on
Yeah. Hello, Fabio Vladimirovich.
Hello.
Yeah, I can go and
you can be seen on the camera.
So
yeah, cool. So very nice talk as always. Thank you. So now you can see me, right?
No, I think
No.
if the camera.
Yeah.
I think it's this camera.
This
Ah,
camera.
okay.
Okay. Now you can see me. Okay.
Yeah, if you sit, because masked veli mi je.
Yeah, mask. I was thinking also about this Fabio's note that he was not able to join us physically. I think that there is one more reason. If you are talking about mobile sensors, it makes much more sense to talk remotely to show the advantage of technology. Okay, so we had a lot of discussions in these directions, and I think Fabio pointed out to several open research. With VG2 representatives, we also eager to run this kind of research in our working group more actively. And I also want to invite to contact us as VG leaders regarding this and also all other working group topics. And of course, you can contact always Fabio about additional questions. I'm now talking in his name. I hope that I guessed what did you want to say to others. Okay, so that's from my side. Fabio, it was great to see you. I'm getting back to work.
So I don't know if there are other questions, comments on this topic or other topics in general that we have discussed today. No, you want to go home.
Yes, it was busy session, but thank you very much. Yeah, so it was quite an interesting and busy session. If there are some items, points to discuss about the topics that we have today, we may discuss now, or we have it also a discussion tomorrow. Is there something to discuss now? Any kind of like last comments, thoughts, ideas?
So Isa made a very general comment or question earlier about what are best strategies for exhausted hyperparameter tuning. How do you really know if you have found the right model? Maybe anyone wants to comment on that. I found it a very general statement.
There was that TensorFlow Greek kind of set was mentioned, but there are also specially designed frames and other things like that are possible to just optimize. And then I think the second question, the second point of Isa was that how can you know that this is the best solution? That probably you cross your fingers and hope for the best. This is the thing, but yeah, I think this approaches like Optuna and similar are quite general and quite well done. I think it's useful to use them.
One thing I'm wondering, many of us gravitational wave people spend a lot of time optimizing template placement, and in a sense this grid search has exactly the same thing. Is that something that people have worked on? Are any of the gravitational wave template placement algorithms useful for deciding how you explore hyperparameters? Is it a totally crazy idea, or have people looked at that before?
This goes into this direction of crystallography, this type of optimal lattices and things like that. I don't know. It's a good question. Yes. No, I'm not. I'm just saying. I recall there are
Trying to search for something.
yeah. So.
So I don't work in template placement myself, so I have no idea about those mysterious darts. But I heard some ideas that, for instance, you could use normalizing flows to do something like that. But I don't know how far this investigation has implemented an idea.
My feeling is that this is very, very case by case dependent, but maybe there are some more general rules. I had another thought that I wanted to mention, but I forgot. But definitely, it would be an interesting thing to research. And tomorrow we will have a talk by Stella about producing, rapid production of waveforms. So this kind of at least partially alleviate this problem. If you can produce the waveforms so fast, then maybe also you can grow the parameters.
I didn't mean using machine learning for template placement. I meant using template placement on your hyperparameter space. Because I don't know what TensorFlow, for example, how it actually implemented grid search, how smart it is. But maybe there's something we've learned in the past few decades that we could help that community with.
Definitely a very interesting idea. Other thoughts? Maybe we should have this kind of session early in the morning so we can shower first. So we can go out, training.
You can do a shower now because it's raining.
It's raining, so it's kind of a shower talk. All right, so if there are no other comments or questions, then we can take it for yet another coffee, and then at 5 we have the screening of the gw1 movie. So as you have heard, everybody is invited. And we'll meet tomorrow at 9:30. So thank you very much, and see you tomorrow or at the movie premiere. Thanks.
Bye.